Thank you to everyone for waking up this morning after the open bar last night. I'm impressed with the numbers. So this work is in collaboration with Robin, who's sitting in the back, and we'll give a talk tomorrow in the quantum mechanics session. This work, although it's been changed from a different session, it's not about quantum mechanics. Actually, a simple problem. And that is, suppose you flip a coin and it comes up heads. What should you estimate the bias P of that coin to be? And we could just stop here and argue for the rest of the 25 minutes about the answer to this question. But I don't think that would be useful because real data is not like this. You don't get to see the outcome of the coin, which is sort of a model for probably lots of things. So let me give you some examples. First, you have engineered noise. So this is applicable to sociological data sampling. So say I want to know how many of you in the audience cheat on your taxes. Raise your hands. Okay. Okay, now mentally flip a coin in your head. If you get heads on that coin, now raise your hand. Okay, so see, this is the sort of example. If I make up some randomization procedure, you are assured some sort of confidentiality. I can go, hey, you raised your hand, you cheat on your taxes, and you say, well, no, my coin came up heads, so I had to lie. Right? Measurement apparatus noise. So, you have this particle detector, and you want to know what is the probability of, a gamma ray coming from some supernova in the next few seconds. Well, you can't really isolate that, and you're going to get different sort of radiation coming and making your detector click. And it's called dark counts or background counts. And what I call intrinsic noise. So a quantum state, there's no measurement that you can do in general that is going to reveal the state of the system. Like when you flip a coin, it gets to be revealed to you what the outcome was. Okay, so this is the situation that we're in. I have some coin that gets flipped. It comes up heads or tails. But you don't get to see that. There's some bit flip error. Okay, you get to see the the outcome of the bit flip error. These two will be the same. This would be like it's heads, it stays heads, it's tails, it's flipped to heads. And if you just multiply these together like you would in high school and add them up, this is the new probability of seeing heads. Okay? And this is the thing that you get to sample from and estimate. Okay, well, here's the sampling distribution of a coin and binomial distribution. Everyone's familiar with that. And well, that new distribution, it's still a binomial distribution. You just have some new bias, right? So, well, what's the difference? Why can't we just estimate this new bias Q? Well, if you want to make predictions about future noisy data, then sure, you just have a new coin with a new bias, and that's fine. But if you want to make predictions about other data, say noiseless data, if you improve your measurement apparatus, or you can give people drugs to make them tell the truth, then no, you can't just estimate Q. And you can see this through a very simple example. So the absolutely naive solution would be, okay, just take count the total number of times you flip this coin and take the number of heads that you see, and you saw that linear relationship between P and Q, just invert that and get your estimate for P. Okay, that's fine. But wait, what happens if you see a fraction of heads that's less than the noise, and you estimate P to be less than 0? Clearly that's wrong. And this happens actually in in the sociological example. It's called randomized response. And typically what you see is you still see everybody saying no, they don't cheat on their taxes. So what should you do? How should you estimate the true fraction of people that cheat on their taxes? Well, you know, in most cases, they just set this equal to 0, or they just ignore that question altogether if there's some, if it's a subset. You know, it's one question out of many that they're asking. So, you know, what's the right answer here? Right. Again, so okay, that's fine. But you know, I estimate P to be between 0 and 1. Well, I'll just estimate Q to be between alpha and 1 minus alpha, and then all my probabilities will be, you know, between 0 and 1. Does this help? Well, it depends on your cost function. And this is, that's sort of the motivation for the rest of the talk. So first I'm going to go through some canonical cost function. Then I'll show you that according to this cost function, the noiseless coin has risk that goes down to 1 over n. So that's good. But if you add noise, you can do no better than 1 over root n. But it's not everywhere. So it's a little bit tricky. It's not straightforward. You can just apply the strategies here to here and just have to be content with some quadratic reduction in risk scaling. And then finally, I'll show you some estimation strategies, which I'm going to call good strategies. Okay, so the cost of seeing some event k, if you have some estimated probability distribution, is minus log k. So this is, if I want to do data compression, then what I'm going to do, I'm going to do Shannon compression, is I'm going to assign the word in my alphabet that I call k, a code word of length log pk. Okay, so that's the cost of event k. It's the length of the code word that I assign. But you know, this cost function crops up in a lot of places, in prediction, gambling, in say philosophy, if you're trying to elicit personal beliefs. So this is one we're going to use from now on. If any of you object, speak now or forever hold your peace.
Let me speak then. I'm not sure I will unless you know what your maximum length k is in a sequence. I mean, this is not very useful because you assign this length, but if you have to transmit this message, the recipient would not know what the particular length is, you know, encoding, so they won't be able to decode it. So, you see what I mean?
I don't follow. I mean, this is.
It works for one event. I mean, if you have one event k with probability pk, you can encode that with one pk.
No, I can do a lossless compression. This one. This is an arbitrary on this side, and assign all my code words this length.
But you can also transmit the length of the code.
I'm not worried about transmitting. Okay. So let's suppose there's some true probabilities. And then the expected cost is the average of the code word lengths that I assign. Okay? And so there's some minimum cost, which is clearly achieved when I estimate my probabilities to be the true probabilities. Okay? So there's some cost that's unavoidable because there's some inherent randomness with these true probabilities. So what I call risk is the additional cost of my estimate. So I take So I take my minimum cost and well, I take my actual cost, right, and then I subtract the minimum cost. And this is the risk. Okay, so what's this difference that I said between the noiseless and the noisy? And I said it depended on the cost function. Okay, so let's take this cost function and see what happens when I have these sort of rare events. So suppose P is very small. Here's my definition of Q. Well, if P is close to 0, this term is negligible. So Q is roughly alpha. Now suppose I have some estimate which is off by some very small amount, smaller than the noise. Then if we compare the P's together, then here is that risk quantity. It's just the relative entropy, if you recognize that. Well, P is close to 0, so this term goes away. This term goes away, and we're just going to be left with 1 log 1 over 1 minus epsilon, and you can all do the Taylor series of that. It's just, okay. So that's the first order term in the Taylor series. Compare Q hat to the true Q, then this alpha is in here now. And you see a contribution from both terms. And, this is something that mathematically can do. Less than a second. You just plug that in and ask for the Taylor series, so I won't go through that. But the first order term will cancel, and you're only going to pick up the second order term. Okay, so if this thing is small, you see that there's a quadratic difference between whether you're comparing the P's or the Q's. So what happens for the noiseless point? I mean, this is an extremely well-studied problem, and this is a technical take on the issue. But if you saw this in a textbook, what would you see? If you think of Sivia, then you would say, well, you start with uniform prior. That seems pretty reasonable, and if you compute the mean and take the if you compute the posterior, you take the mean of that. This is what you get. Okay, this is the Laplace's famous solution to the coin problem, which is equivalent to any sort of dichotomous event. Say, what's the probability of finding an elephant on Mars or the sun coming up tomorrow? Well, just because you haven't seen it in the past doesn't mean you should assign that 0 probability. He says you should add some dummy counts, say, pretend that you saw it once, and that sort of hedges your bets. But of course, I mean, this is not unique. It's been suggested that there's you could use a whole family of these linear estimators, right? Just adding some beta instead of 1 here. And this all works out really nicely because these come from a conjugate prior to your sampling distribution. So if I take this prior and I compute the posterior and I find the mean, I get this value for my estimate. Okay, but the risk depends on the true probability, P, which we don't know. So how do we get rid of this dependence on P? Well, the sort of full Bayesian solution would be, start with prior, wherever you get it from, and minimize the average of this risk with respect to that prior, and take the argument to that, and that's your Bayes estimator. Okay? For all sorts of risk functions and domains of interest, this, for all practical problems, this would be the mean of the posterior. Okay, so the other solution is find the maximum of this thing, and then minimize with respect to possible estimates that maximum. And this is called Minimax. So you might think of this as the frequentist solution. Now, it happens that for this problem and lots of problems, there is indeed a prior for which these two are equal, and what you might call the frequentist solution and the Bayes solution coincide. And for this problem of estimating the bias of the coin, these priors are damn close to it. So what do I mean by that? Now, if I take some asymptotic expansion of this risk, I can show that it's at least a half 1/3. And the best possible linear estimator happens when I add beta naught, which is 0.0509, which is really close to a half, which is the Jeffreys number. And this thing has risk equal to beta naught 1/n. So you see the difference here is very small. Okay, this is a tight lower bound. You can achieve that. Okay, so here's the bias of the coin, the risk, the minimax. You can't get a curve that has a lower maximum than this. And here's adding a half. Right, so there's some small difference, but they're very close. Okay, so it's early in the morning. I'm not going to go through the proof of this, but I can show that for a noisy coin, the minimum risk goes as 1/√n, and there's some constant that only depends on the noise. Here is that plot I just showed you, the minimax risk of the noiseless coin. This is for 100 flips of the coin. Here's 10% noise, quarter noise. You see the risk goes up, and okay, so now I said that this risk isn't necessarily everywhere. There's this sort of unique behavior at the boundary. So here's my minimax risk for the noiseless coin. And here is a minimax risk for the noisy coin. Again, this is for 25% noise. And here's if I just took the Bayesian solution with Jeffreys function. So this behavior is very typical. If I take some prior, I can find some number of flips of the coin where that prior's risk is dominated at the boundary, and is nice in here. So why is that? Well, this black line that goes straight down, that's the maximum likelihood solution. So here I see this many heads, and this is the estimate I should have. So for 10% noise, if I see 10 heads, then maximum likelihood says I should estimate 0 for everything less than 10 heads, and then be linear for all other. Jeffreys just sort of edges you a bit at the boundary. In Minimax, what is it doing? Well, it edges you a whole heck of a lot in the interior just to bring this risk down at the boundary a little bit. So we thought about can we get some idea of what the intrinsic risk of a bias is? And the idea was take some prior which is supported on 2 points. So pick a point and some other arbitrary point, and some arbitrary weight in between. And we say that the intrinsic or bimodal risk of some point is the worst phase risk when I can change its sort of foil bias and the weighting of that bias. And I call that the intrinsic risk of some point. And it's indeed a point-wise lower bound of the minimax risk. Okay, so what's that look like? So here's Laplace, that at the boundary, here's minimax, and here's the intrinsic risk. So I want to find some sort of estimation strategy whose risk profile looks like this, rather than this. Because this one, you'll see that it achieves the best it can do at the boundary and at the interior. Okay, so how much time do I have? Just okay. So here's a noiseless coin, and here's maximum likelihood. It just goes from, if you see 0 heads, you estimate 0. If you see 2 heads, you just estimate 2 over the number of flips, just straight. Adding a half just edges you a bit. And minimax, what does it do? Well, it just does something funny at the boundary, and then it's basically linear everywhere else. Okay. It turns out that for noiseless coins, there's this this equivalent strategy to these linear estimators, and that is you take the likelihood function and you take some hedging function, and you multiply them together, and you take the maximum of the hedging function of the likelihood function. So this is a strategy that Robin applied to quantum state estimation, and for noiseless coins, it turns out that these are indeed the linear estimators. And if you do this for noisy coins, well, there's an analytic solution. It's some solution to some cubic equation, so I don't want to write it down. But, I mean, this is a solution, and it's analytic, and you can just write it down. Take a page, but there it is. And let me show you what the risk profile looks like. Well, there's the Minimax. You know, it's doing the best it can do. There's no curve that can have a lower worst case than this. But it sort of achieves this everywhere. It tries to be flat. If it can be flat everywhere, it will be flat everywhere. And that's, you know, in the bad region. But we said, well, the intrinsic risk should be only bad at the boundary and be very good in the interior. Well, there it is. There's the solution that we're looking for. Some strategy that only does bad where it has to do bad and does good everywhere else. And sort of show you that the worst case will always be achieved at the boundary. So that's this. And the best will be achieved, you know, as n gets large enough, will be achieved right in the center of this line. And these black lines, this is 1 over root n, and this is 1 over n. So you see that this is the strategy that's doing what we want. And moreover, and this is very nice, and I have been accumulating more and more numerical evidence for this, the optimal hedging parameter that you should use seems to be independent of n and the noise. So there's just some beta that I can tell you. There's an analytic solution, and this will be just a nice plug-in strategy that you can use. You don't have to do any optimization problems. And you will sort of be doing good. So what did I tell you? I said, you know, we're going to be using this relative entropy loss. The noiseless coin has scaling 1 over n, that's good. Noisy coin 1 over root n, that's bad. But the bad part is only at the boundary. You can achieve good risk in the interior, and I gave you some estimation strategy which achieves that. So these slides are all contained in this little thing. If you take a picture, including this slide itself, so I don't know if there's any sort of information. Think about that. So take a picture, and thank you very much.
Thank you for your flexibility, first of all, in switching the schedule. I should point out that if you look carefully at the schedule, you'll see that this is an instance of quantum uncertainty because the time is listed as 9 to 9:30 a.m., so there was a superposition with obvious at the top. Are there any questions? Let's go to.
Okay, hi. This is going to sound critical at first. It's not, okay? There is nothing in the sum rules and Koch rules of probability theory which say maximize anything or minimize anything. There's some Koch rules. So those only come in when you're wanting to compress your what should be a Bayesian posterior, Bayesian inference, into something for future use. And there, of course, you can use whatever rules you want, and I'm quite sure what you're doing is perfectly reasonable. I'm just hoping that other people don't think that there's something philosophically magic about minimization and maximization. These are just nice tools to get out of boxes.
Just a matter of clarification. Maybe I misunderstand your definition of noisy coin. To me, doing the core experiment, the data has no noise. You either have a head or tail, right?
Okay.
So there's no uncertainty in terms of outcome. So tail, there's no uncertainty, just tail.
Okay, suppose I flip the coin, but you know me to lie 25% of the time. That's the idea. Or there's some mechanism which flips. I mean, you record the outcome, and then you put it out in some system which is exposed to some bit flip error, something like that. Of course, if you flip a coin, you get to see that it's heads. That's not the situation we're talking about. We're talking about the situation where you flip the coin, you don't get to see the outcome. You get to see someone's report of the outcome, which is exposed.
So this is actually just more of a comment. I wanted to comment briefly on John's question or comment. Just to amplify what you said, all the admissible estimators for this risk function are indeed Bayes estimators for some prior, and they're the mean of the posterior. So if we want to do the absolute best thing, not only the Minimax estimator, but all of the admissible, all the good estimators, all the best estimators would be Bayesian with some prior. But particularly for multidimensional problems, of course, that integration gets really hard. And so part of the goal was to find a very computationally easy ad hoc approximation that comes very close to those good Bayesian estimators.